We build castles in it, we play in it, we bury our toes in it, but what is sand? And what types of sand are there? Is there so many different colors on the screen right now? What the heck makes up these grains? So for this video, I will hopefully answer the question of what is sand, the different sources of sand, and then we'll go one by one through many different types of sand, which there are 10 plus types. I did not expect that until I was researching for this video. And then I'll talk a little bit at the end about uses of sand for both humans and other organisms. Sand has various compositions, or what it's made up of, which is why there were so many colors on that title slide, but it's actually defined by grain size. Like I mentioned in a recent short I did, did I just say grand? Sand sits between the other grain sizes in geology, such as gravel, which is bigger than sand and can be broken out into granules, pebbles, boulders, all of that. And then below sand, there's silt and clay. And the composition, the makeup of sand, depends on local rock sources, so where the sand came from or what rock broke down to make those sand grains, as well as environmental conditions and kind of intensity of the environment. Two major classes of sand depositing environments exist. These are beaches, and then we have desert or aeolian environments, which also are heavily dominated by sand, or oftentimes. Not all of them, but many of them. So what are the sources of sand in these environments? Well, it's just erosion, basically. Rocks erode over geologic time as they are transported by water or wind, and the composition, as I mentioned earlier, depends on the original rock and then also the intensity of the environment. For example, the most common sand-forming rock is granite, which is why the most common sand constituent is quartz grains or silica grains. Basically, the feldspars of the granite, granites, by the way, are just igneous rocks that are mainly composed of feldspar and quartz. And the feldspars typically dissolve, leaving behind just the quartz fragments, but you can have more feldspar-rich sand depending on the intensity of the environment. And when you have a really quartz-dominated sand or beach environment, it's very white. And when you have more of the darker feldspar and lithic grains, that's what the darker grains are called, then you have a more tanner beach, which we've all seen kind of ranges in beach color. However, I should mention that there's also impurities in quartz that can cause tan or goldish beaches, even when the beach is quartz dominated. And I'll talk more about that later, but they're typically iron impurities that make it look corally or orangey in color. So in regards to the desert or aeolian type of environment, sand dunes form because of the dry and windy conditions. The Sahara, for example, is known for its vast sand dunes, which exist mainly due to the fact that there's a lack of vegetation and lack of water. Over time, the wind blows away finer particles like clay and silt and dead organic matter and leaves behind smooth, round sand and larger rocks. If you want to know more about dune structures and dune forming processes and the movement of grains in desert environments, I have a whole video about aeolian processes and depositional conditions, and I'll link that to the top right if you want to check it out. Beach sand, likewise, forms due to erosion from constant wave and sediment motion, and weathering, river deposition, and marine life also accelerate the process of beach formation. Now, here is kind of a diagram showing the different types of beach depositional environments depending on what's dominating that region. For example, you can have a wave-dominated estuary versus a tide-dominated estuary. There's a whole bunch of different structures and types of kind of environments that form depending on what's dominating that environment. So check out my shoreface, tidal, delta, and estuary videos, all separate videos, for more on those structures. I'll link the tide one to the top right because I think that one is the one where I go over the most of like the differences between wave and tide dominated systems. But for this video, we are going to be focusing on the different types of sand because Goodness gracious, there are many, which surprise the heck out of me. Again, sand is a grain size, so it can have many different compositions. I remember when I took carbonate petrology, my professor really stuck to the definition of sand because every time he was like, "What is this?" and I said sand, he was like, "That's not a composition. That's a grain size. You need to give me a name before the sand. Is it quartz sand? Is it carbonate sand?" And man, by the end of that class, I never called sand just sand ever again. So the types of sand include quartz sand, which can be white to gold, as I mentioned earlier, basaltic sand, which is black sand, which is really cool, carbonate sand, which can be a range of colors from pink to tan to white. And this includes things like ooid sand. Ooids are carbonate coated grains, and I'll talk about those later and how they form. We also have foram sand or foraminifera, which are organisms. They're just single cellular organisms, so they're very tiny and they can form a majority of sand, as can coral fragments and coral pooped out of parrotfish. Yes, that's right. If you've ever watched a documentary about coral reefs, they probably mentioned that parrotfish eat coral and poop out sand, or what they call sand, but that's only one type of sand. That's not all sands. So not every beach you go to is poop. And so keep that in mind. Gypsum sand, which is really white and close to my heart because gypsum sand is a major or the major constituent of a certain place that I love to go, and I live somewhat nearby, so I'll talk about that later. Olivine sand, which is green and beautiful, yet rare, and human sand, which I didn't think about, but when I was reading up for this video, that is what a lot of people list as another type of sand. They list it as different names. I'm calling it human sand because some people talk about human glass forming major, sand deposits. Some people talk about plastic in sand. So I kind of combine the two into what I'm calling human sand, and I'm going to talk a little bit about where it occurs and its impact. So let's talk about these individually now. First, we'll start with quartz sand. Quartz, again, I mentioned earlier, is the most common constituent of sand. It's just SiO2 or silicon dioxide, also called silica, and it's very common because it's resistant to both chemical and physical weathering. It not only is very chemically inert and hard to dissolve, but also it's very hard to physically break down because it's just hard. It's a hard mineral. And that's how we know that sand that's dominated by quartz is likely very old and has traveled a far way from its source area, because if it hadn't traveled that far and it wasn't very old, there'd probably still be abundant feldspar and other fragments within the sand. But when it has traveled so far and it's very old and gone through a lot of weathering, all of that other stuff has dissolved away because it's not as resistant as quartz, and the quartz is left behind. The long journey is required to allow erosion to break down grains to sand size, and also to allow weathering to dissolve the more soluble minerals such as feldspar. Quartz sands are typically found on passive continental margins where there's a lack of active volcanism, because if you're getting a lot of volcanism, you'll probably get a lot more either very young sand with a lot more lithic and feldspar fragments, or even basaltic sand if the volcanism is basaltic, and I'll talk about that in the next slide. And so good examples of quartz sand can be found in Florida, and as we can see on this map here of passive versus active margins, this makes absolute sense because Florida is in the passive blue zone, and all of these pink zones are active, so they have less old, mature quartz sand beaches and are probably more, darker in color because they have a whole bunch of other fragments from active volcanism. Now moving to black sand, which is super cool. I've never been to a black sand beach, but I want to go. Black sand is basically found near volcanoes, specifically basaltic or more mafic volcanoes. So volcanoes that spit out material that is darker, basically. And that's because basalt is black. And, and when you break down a black rock, it forms little sand grains that are black. The reason that basalt is really dark in color is because it contains a lot denser materials than things like granite. Granite is very what we call felsic, and that's very light in color because it contains a lot of silica, which is light in color, and feldspar, which is light in color, whereas basalt contains a lot of heavier mafic minerals that are much darker in color and much less silica, although it does still contain some silica. And because they are so black or so dark in color, the sand gets so hot on these black beaches that if you walk barefoot on them, you could even burn your feet. Now, black sand is made from the interaction between lava and seawater, and typically black beaches form from a single eruption event, and so therefore they can be pretty short-lived compared to other beaches that are continually being replenished by either organisms or erosion. For this reason, Hawaii has made it illegal to remove black sand from their beaches. Another cool tidbit about black sand is that if it contains enough magnetite, which is a dense iron mineral that can be present in basalts, then it may be magnetic. I don't know if you've ever played with magnetic sand, but it's, you move around your magnet and the sand follows it. That's so cool to me. I loved that as a kid. Now moving to kind of the opposite end of the spectrum in terms of color, and that is to Ooid sand. Now, Ooid sand is that first category of carbonate sand I talked about. Calcium carbonate is the main constituent of carbonate sand. It basically is produced by corals and coral skeletons, forams and foram skeletons or tests, mollusks and mollusk shells, and what we call ooids. And this carbonate mineral is the most common constituent of sands in areas that have major reef ecosystems, because that's where all of these organisms are producing the carbonate. However, ooids are not forming in the reef per se. They're not even biological. They're actually formed abiotically. They are small, round, carbonate-coated grains, and they grow by accretion in shallow, wave-agitated water. The waves move them back and forth with the swash and backswash of the water, and as they move back and forth, these grains, they get coated and coated in this calcium carbonate, and this makes ooid beaches very unique because instead of shrinking or eroding to become sand grain size, like many beaches, such as quartz beaches, you have the grains growing to sand size to make up the beach rather than shrinking. I do want to mention, however, that coral reefs are common in the Bahamas, and coral fragments and other organism skeleton and test fragments make up a large component of the beaches there. However, I will say that there are some regions where if you collect sand, and I only know this because I haven't been there, but in my carbonate petrology class, we had these little sand slides. They put sand on the slide, we looked at it in the microscope, and we identified all the grains, which if you haven't ever done that, like, highly recommend. Very cool when you actually look at sand through a microscope, especially carbonate sand, because there's so many little organisms that are really cool. But I will say the ones that were from the Bahamas were especially rich in ooids. So they looked like this little pearly type of sand. It was really cool. Now moving to another type of carbonate sand, or another constituent of carbonate sand, and that is foraminifera or foram sand. So foraminifera are these little tiny organisms, unicellular protist organisms, and they have tests or shells that can be quite elaborate despite them just being single-celled organisms. They're typically made of calcium carbonate, but can also be made of agglutinated sediment, so other sediments that agglutinate together to form the organism's test. But it's my understanding, I think, that these agglutinated organisms or forams live in deeper environments, so I'm not sure how much they would make up the sand. I think the sand is mainly the calcium carbonate type, and they are typically less than 1 millimeter in size, but can reach up to 20 centimeters. I mean, I can't even, there's one cell. I mean, the cell doesn't reach that size, but the test does. The shell around the cell reaches that size, which is pretty crazy. Obviously, at that point, it's no longer sand, but in the region of less than 1 millimeter to 2 millimeters, it is sand. And moving to the third and final type of carbonate sand on carbonate beaches, you have parrotfish poop or coral sand. Now, I do want to specify that coral fragments can make up sand that never went through a parrotfish, but there is a lot of coral sand that has gone through the digestive system of a parrotfish. So basically, parrotfish have abrasive and fracture-resistant teeth that allow them to eat coral. Why the heck are they eating coral? Well, they eat it to get nutrients from the algae that's in the coral. But the coral itself, the carbonate skeleton of the coral, is not useful for the parrotfish. So they get their algae and they poop out the coral part that they don't need. And this poop makes up white grains of carbonate sand that makes up a surprising amount of carbonate beaches. Now moving to gypsum sand. So remember when I said there are two major types of sand depositing environments, including beaches and deserts, where the sand is in both cases formed by erosion? Well, gypsum sand is different. It is more so a desert environment, but instead of forming by erosion, the grains precipitate from solution. So what does this mean? Well, White Sands National Park is a perfect example of the process that forms gypsum sands. I've been visiting White Sands since I was a little kid, and I love it. Here's a picture of me and my cousins and brother at White Sands just a few months ago. So it's an incredible place. I mean, look at this picture here to the right. Like, it extends for miles and it's so, so cool. And the dunes are just so pure. It's amazing. But like, how the heck did it form? How did that happen? Well, gypsum is an evaporate mineral. This means that it precipitates from solution when evaporation overconcentrates or oversaturates a solution in the ions that make up gypsum, which are calcium and sulfate. For the case of White Sands National Park, the nearby Alkali Flat and Lake Lucero are the sources for the gypsum that makes up the dunes in the actual White Sands dune field. For example, in Lake Lucero, after heavy rain, as shown in the picture below, gypsum precipitates during the evaporation and oversaturation of the water in those ions, and eventually this gypsum is carried by wind to the dune field where everybody goes to visit, and gypsum is, because of its relative solubility in water, otherwise very rare in sands. Another really beautiful type of sand that I have unfortunately not gotten to go see in person, but hope to eventually, is olivine sand. Now, olivine is a green ultramafic mineral. That just means very dense igneous mineral that is very unstable under oxic atmospheric conditions or our well-oxygenated atmosphere, and therefore weathers very quickly. And it weathers into these tiny, tiny little crystalline grains of olivine that are just this beautiful green crystalline color. And sand containing olivine typically occurs in volcanic regions because it is this ultramafic volcanic mineral, or plutonic rather than volcanic, but I won't get into the chemistry here. It just is sometimes present in volcanic regions, but it is rare in terms of, making up full beaches like this one that is very green. But the reason that beaches like this can form is because olivine is much denser than other silicate minerals, and the density difference between these minerals allows waves to separate olivine from the rest and concentrate it at the beach, which is what happened for this beach. Now, finally, moving to human sand, or glass and plastic in sand. Now, glass I'm not going to touch on mostly because it's very similar to quartz sand. I mean, we make glass from from quartz sand. It's just silica, but plastic is the major thing it's different than anything else in nature, and it can't be fully broken down. So it's very much more human-y than glass is. And you might not think that there is that much plastic on beaches, but when I read this, I was just blown away. Apparently, there is about 18 million tons of plastic on Henderson Island, even though this island is thousands of miles from any major landmass. And yeah, we all know that plastic isn't good for wildlife, but as it turns out, it also affects sand temperature. Sand with moderate levels of plastic have been shown to have higher maximum daytime temperatures and lower minimum temperatures. Sand temperature can also affect life by affecting heat-sensitive crabs, mollusks, shorebirds, turtles, iguanas, anything that's living on or in the sand. For example, sea turtles bury their eggs in the sand, and research shows that higher temperatures of the nest of eggs can decrease hatchling fitness and success. Finally, moving to the last few types of sand. I only had time to mention the major types, so now I'm going to mention honorable mentions that are also types of sand, but not either as common or as commonly thought of sand. For example, snow. I just filmed a video about ice and how ice Ice is a mineral, therefore snow, which is made of ice, is a mineral, and can be sand grain sized. So technically, snow that is sand grain size is sand. That's one of the honorable mentions, as is arkose or arkosic sand, which is sand that, comes from typically granites like the quartz sand, but contains a lot more feldspar. Hematite or iron stained sands or coated quartz sands may have a yellowy or orange color due to the iron staining. Chlorite glauconite sand is another type of green sand, similar to the olivine, but instead of the olivine making it green, it's the chlorite and glaucophane making it green. But from most of the examples I can see, these minerals are typically more of a bluish greenish, and olivine is definitely more of a yellowish greenish. It's a very green. And then garnet sand, which is rich in garnet and reddish because it's made of garnet. Lastly, I want to talk about the uses of sand because, as I mentioned earlier, sand is a non-renewable resource on human timescales. It renews itself on geologic timescales, but on our timescale on Earth, it's a non-renewable resource, and we use it for many things, including construction. For concrete, for example, 50 billion tons of beach sand is used per year for construction. Desert sand, on the other hand, is plentiful but not suitable for concrete, so we use beach sand for that. For bricks, sand is mixed with clay and other materials. And glass, we use silica sand to make glass. Abrasion, before sandpaper, we used wet sand. Roads, sand improves traction and is used often in icy and snowy conditions. Agriculture, sandy soils are ideal for certain crops, and their drainage characteristics make them very suitable for intensive dairy farming. Landscaping, sand can be used to make small hills and slopes, used often in golf courses and golf course landscaping. Beach nourishment, often beaches where tides and storms or deliberate changes to the shoreline erode the original sand. We can add sand to nourish the beach in that way. And fracking, silica sand is used to hold open cracks in fracking. Air filtration, fine sand mixed with cloth used to be used for certain mask filter designs, but now has been largely replaced by microfibers. Water filtration, commonly water treatment plants use sand filters. Sandbags protect against floods and gunfire. Recreation, we, play beach volleyball, we, play in sandboxes, we make sand castles, we slide down sand dunes like I do at White Sands. We mix sand with paint to produce textured finishes for walls, ceilings, and or non-slip floors. And we use sand for the base material of our aquaria. So we use sand for a lot of things. However, humans are not the only ones who use sand. As mentioned earlier, turtles and other reptiles bury their eggs in the sand. Many shore-face animals burrow into sand to eat or live or hide from predators, etc. Desert life also burrows in the sand occasionally, but typically to hide from the intense sun rather than to eat, live, or hide from predators. Some animals and microbes even build kind of skeleton-like structures for protection using sand and other sediments. For example, microbial mats like these stromatolites here form not because the microbes themselves are a hard, rigid structure, but rather because there's an incorporation of sediment into the structure to make it hard and rigid and protect the microbial communities. Lastly, and my most favorite use of sand and, fragments like shells and stuff by animals is in some pufferfish. They use sand, sediment, fossil fragments, and, mollusk shells to build structures and shell collections that will impress potential mates. So they use it for mating. And I saw a nature documentary not too long ago where this fish was building a shell collection to impress this female fish, and this other male fish came over and was taking his shells from him. And I felt so bad because the other guy that was getting stolen from had no idea because he was out getting another shell. And this other guy, his neighbor, was just taking his own shells. And the guy would come back and put a new shell and probably be like, what? Didn't I just put a shell here? So anyway, that's all I got for sand, you guys, or the different types of sand and stuff. Obviously, like I mentioned, I have other videos that talk about sedimentary structures and depositional processes. In fact, I'll link my sedimentary structure video up here for you guys if you want to see the kind of structures that form in sandy deposits and why they form and what they mean when we see them in the rock record, all of that. And if you guys want to check out my sedimentary and stratigraphy playlist, I'll also link that here for you. And as always, you can check out my references down in the description box below. And with that, guys, thank you so much for watching, and I'll see you guys in the next one. Bye.